Thank you, Michael. And today we're going to talk about gallium nitride transistors. They've been out in the marketplace now for over 4 years, and we're crushing silicon one application at a time. Today's topic is going to be wireless energy transfer, and we have Michael Rooi to take over from here to give us a view of where the state of the art is and how efficient we can really be with wireless energy transfer.
Thank you, Alex. Thank you, Michael. So let's get right into it. Today's agenda, we will cover an overview of wireless energy transfer for those who are not familiar with it. And then we will go into the wireless energy topology overview. We will discuss 2 topologies. And then we're going to discuss why eGaN FETs for wireless energy and showcase the performance benefits that they produce. Then we'll go through the experimental performance and show them the performance that they yield, and we'll summarize at the end and have a look into the future. And we'll close out with some questions. Let's take a look over the overview of wireless energy transfer. First of all, we'll look at the magnetic field wireless energy transfer. Basically comprises 2 coils, and one coil generates a magnetic field that is picked up by a second coil, and this yields an air core transformer with a corresponding model on the right-hand side. And this will be used as a foundation to move forward. We will talk about highly resonant wireless transfer. This is the technology that is used to enhance the energy transfer between the 2 coils because the distances are great and there's no magnetic material to conduct the flux. So we have to find other means to overcome the large leakage inductance that is produced by this transformer. This is typically done using matching impedance networks that is then connected to the coil and causes it to resonate at the frequency of operation. The 2 coils are matched with their own inductances, and then we, at the device side, we simply rectify it and smooth it out with a capacitor. The coils are therefore tuned to resonate at the 6.78 megahertz, which is the frequency of choice at this point in time. We'll get into the details later. Both series and shunt tuned can be used. The series tuning will decrease the impedance as seen by the load or the amplifier, and shunt tuning will increase the impedance. So between the 2, the impedances can be very easily controlled. And the coupling and load variation, however, can shift the resonances, and we will show the effects of that on the amplifier and the load. Why wireless energy? It's a great question, and many people have asked that. First of all, we'll look at mobile device charging. It's a convenience factor, and many people are tired of having cables, and the multitude of devices that have encroached on our lives make it that it is very cumbersome to have lots of wires everywhere to charge your devices. And the second part is it extends battery life, as you can charge very easily, and simple mats can be placed at many locations that can help charge or just give a little boost to your device. The second application is medical implants. This is a very important part because it improves quality of life for many patients, particularly if they need implants that need to be powered. And those are typically done through a cable through the skin, which is a site for great infection. So what the wireless energy enables is that there's no penetration of foreign objects through the skin of the patient, and therefore it is a wonderful way to extend the life of the patient. And then the third area where wireless energy is proving good is the hazardous environment areas, such as explosive atmosphere, corrosive locations, or even high voltage. You might have to add a small sensor to a high voltage line or something, and this is a great way to do that. For corrosive locations, it could be under the seawater or something like that, where connections are a very bad idea. And explosive atmosphere is fairly obvious. If you have a connection, you make or break, and you generate even a smaller spark that can be very dangerous. Challenges to wireless energy. Let's have a look, and there are numerous. The first one is high efficiency. mainly limited to the dissipation budget, primarily driven by the cell phone industry, smartphones, but also it's driven by the energy standards such as Energy Star that require a certain amount of efficiency for these systems. Low profile, again, driven by the mobile market. We don't want a nice, sleek smartphone to suddenly turn into a large clunker simply because it can be wirelessly charged. And the robustness to dynamic operating conditions. This is the convenience factor. Users do not want to have, oh, it must be placed exactly in this location, in this orientation. It needs to be just simply thrown on a mat or even in proximity of a mat, and then can be charged. And these add a lot of challenges to the system. And of course, foreign object response. What happens when you put your keys on the mat, or if you accidentally put this on a solid metal plate? What is the response to the system to those kind of unexpected conditions? And of course, lastly and not least, is the regulatory compliance. With anything electronic, it has to go through a series of tests to make sure it's safe and complies with certain regulatory standards, and we will discuss those as well. Let's have a quick look before delving in. Is the wireless energy system. It comprises of 4 main sections, and the terminology can become familiar or unfamiliar, but we talk about the power converter or the amplifier, which is the circuit that drives the source coil, which is the second component, and it is the transmitter. It transmits the energy and includes matching to improve or enhance the transmission of the energy and to overcome the large leakage. Thirdly, we have a device, which is the receiver. It also includes matching, and it receives the energy and catches as much of it as possible. And of course, the fourth component is the rectifier with high-frequency filtering. In some cases, it may include a post regulator to make sure that it will operate for standards such as USB and other power requirements. Let's have a look at some of the compliance requirements, primarily driven by the radiated emission standard. The ISM band, the Industrial, Scientific, and Medical band, has been identified as candidates for transmitting the frequency, as it's an unlicensed band and not subject to very difficult licensing for products. The frequencies that have shown up to be the most popular is 6.78 megahertz with a bandwidth of plus minus 15 kilohertz, but in some areas is subject to local restrictions, so it's not widely accepted in all locations. 13.56 megahertz has no restrictions, but the bandwidth is narrower and is also proven to be a popular frequency of choice for wireless energy. No power limit has been specified that can be found, but there are issues that can be arising from too much power at these frequencies and include induction heating into metal objects even at certain distances if you go too high in power, or even inducing unwanted behavior in certain other appliances, which is technically not permitted. FCC and the European standards govern the intentional radiated emissions, and they must comply with those standards, in particular the FCC Part 15 and the European Standard 55011. Wireless energy standards are also emerging. First, we have the Alliance for Wireless Power, the A4WP, now known as RESENS. Highly resonant energy transfer based type of system for loosely coupled coils. The other wireless standard is the Wireless Power Consortium, or the G standard. It's typically the lower frequency and is tightly coupled and inductive based standard. The two standards here do not have much overlap between them, other than they use magnetic fields to transfer energy. And lastly, the Power Matters Alliance has recently joined forces with the A4W standard, as they are pretty similar in structure. Let's have a look at some of the wireless energy transfer topologies. as we go deeper into the discussion. We will look at a single-ended Class E. The Class E has been proven to be a very popular topology of choice for wireless energy, as it theoretically has a 100% efficiency for the transfer. But we will go into the details of its shortcomings. And then we'll also introduce a new zero voltage switching voltage mode Class D amplifier and show that it's been enabled with the use of GaN FETs. Before we get into the topologies, we want to make it simpler to understand these topologies. So we're going to take the entire coil set, which is untuned on the source side, but tuned on the device side, and it will include the rectifier, output capacitance, and the DC load, which can vary. And we will lump that all into a single complex element, and we call that Z load. So whenever you see this symbol, this is what's behind that symbol. So let's get into the Class E. On the left here, we have the schematic for the Class E topology, and you can see again the Z load has appeared at the right-hand side of the schematic. The ideal waveforms are shown on the right, and essentially we have a number of components that sets up resonances so that we have a voltage and the current at two different frequencies for resonances, and they establish the necessary conditions for zero voltage switching. However, if the load impedance shifts too much from the optimal design point, which can happen in a wireless energy transfer system, we will show that the peak voltage across the device can increase dramatically, and even the conditions required to maintain zero voltage switching can be lost. The switch fault rating in this case for the optimal operation is around 3.56 times that of the supply. The output capacitance of the device is absorbed, so to speak, into the matching network, which comprises the shunt capacitor, CSH, and the extra inductor, LE. Those two components is technically not absorbed, but it is part of the circuit and is therefore very important in choosing the right switch for that topology. However, this topology is susceptible to load variation and can lead to high FET losses as the zero voltage transition is lost, and there are two conditions for that. One is when the load becomes too inductive, can lead to excessive diode conduction. And secondly, if the load is too capacitive, it can lead to excessive capacitive switching on the device as the circuit goes from zero voltage switching into partial zero voltage switching. And then, of course, the actual voltage that's applied to the tuned coil, in other words, CS and Z load, is approximately 0.7 that of the supply voltage. Let's have a look at the zero voltage switching voltage mode Class D topology. In this topology, we have a half bridge switches configuration, and again, we see on the right-hand side CS and Z load, they're tuned for operation for the coil, and then the ideal operating waveforms on the right-hand side. And this topology differs from the classic voltage mode Class D in that we have a zero voltage switching tank circuit made up of LZVS and CZVS, and that is used to operate as a no-load buck converter and establishes the necessary current in the circuit to allow self-commutation of the switch node voltage between Q1 and Q2 for both switching edges. And this allows the converter to operate with very low losses. The switch's voltage rating is that of the supply. The output capacitance is transitioned by the zero voltage switching tank, and the zero voltage switching tank also does not carry the full load current as the inductor, the extra inductor, and the RF choke does in the Class E topology. Therefore, the corresponding losses in that inductor are also significantly lower. The coil voltage, however, in this case is half that of the supply voltage, slightly lower than that of the Class E case. So let's have a look at GaN FETs for wireless energy transfer. Why do we want to use GaN FETs? First of all, they have low input capacitance and low output capacitances. That is important for maintaining low losses and designability. They also have lower RDS on for equal voltage rating compared to MOSFETs. So that equates to lower conduction losses when using this devices of equal design. They're also low profile. They're very small devices. And of course, there are gate drivers available now that can be used even at these frequencies, the LM5113, 5114, and the UCC27611. All of these gate drivers are quite capable of operating at the 6.78 megahertz. Let's have a look before we get into the topologies and how to compare the various technologies. We're going to look at a wireless power figure of merit. All the topologies are zero voltage switching. Even when they operate off the optimal operating point, they are very closely aligned still to zero voltage switching operation. If not, the losses in the devices become so excessive that it would no longer function. Therefore, for the gate charge, we can omit the voltage transition portion of that by simply deducting it from the total gate charge, and that can be used as part of the figure of merit. The output capacitance is essentially absorbed into the circuits of both the converters and is therefore excluded. However, it is still important because it drives off-resonance losses. In other words, when you have coupling and load variations, what happens to the circuit's performance is driven by the amount of COSS that you have. So it's still an issue there. And particularly in the case of a Class E, it determines design ability. If you have excessive COSS, you cannot realize a good design over a wide operating load range. So here we have a figure of merit for wireless power transfer, which is simply the on resistance multiplied by the gate charge without the voltage transition component. Let's use this now and compare some devices with some MOSFETs. So here we're comparing for the Class E, a 200 volt EPC 2012 against a 200 volt MOSFET in a power 3 pack, which is 3 by 3 millimeters, very small little device. To my knowledge, there is no MOSFET available at this voltage that can operate with a logic gate. So there's one disadvantage already that the GaN FET has over the MOSFET. And secondly, the voltage must be chosen higher than expected for power level, because it might turn out when you do your optimal analysis and design for your circuit, you say, oh, 100 volt MOSFET or device is sufficient. But as soon as you vary the load and as soon as you change the coupling factor, you will see that the operation of the Class E will deviate from the ideal, and the voltage across that device can go as high as 6 times the supply voltage, necessitating a device in excess of 150 volt capability. On the right-hand side, we have the zero voltage switching Class D comparison with 2 EPC devices, the 8009 and the 2007, compared to 2 MOSFETs. Both MOSFETs are very similar, and the one is a logic level FET, that's MOSFET 2, and the other is a regular gate voltage level. However, the MOSFET, which is logic level, has a much higher on resistance and is comparable to that of the EPC 8009. And the MOSFET 3 shown there has a much lower RDS on component and is comparable to the 2007. As you can see there, that it's the gate charge between the two that still drive up the figure of merit to be higher than that of the GaN FET. Let's use this wireless power figure of merit to come up with an optimal device for the Class E amplifier based on a 30-watt wireless system into a load. And we can see here, using the figure of merit, we can then vary the on resistance for the device and calculate the anticipated device losses. When we go to the left side of the curve, we become gate drive power dominant as the gate becomes very capacitive as the RDS on is going down, and the losses in the gate drive and the gates circuit will increase. On the right-hand side, we have a linear rise in the losses of the device, and that is primarily driven by the on-state resistance of the device. Now, you can see from this analysis here that there's a huge difference between the two technologies shown here, and that both of these are not optimal either. The MOSFET can benefit from an increase in RDS on as the gate driver losses are being dominating here. In the case of the eGaN FET, it shows that the eGaN FET can be improved by decreasing the on resistance somewhat. But as we will see later on through experimental verification, that is not entirely true, because this figure of merit, as I mentioned before, does not take into account the output capacitances. And pushing that point further down to optimize the losses themselves pushes it into the area where the circuit cannot be realized over a wide operating load range. So too low RDS on yields too high output capacitance to realize the design, and that's probably the case that's true for the MOSFET as well. Let's have a look at the optimal device for the zero voltage switching class D. Here we compared the two technologies again with between 4 devices. The EPC 8009 is a 65 volts device, and the EPC 2007 and the other 2 MOSFETs are all 3 100 volt devices. You can see the impact of the change in the logic level gate to a standard gate from 5 volt to 10 volt, how much it impacts the losses for the device that is consumed. These power devices, the device power includes both the conduction and power switching losses and the gate charge losses and the necessary overhead to operate the gate driver. As you can see that the EPC 2007 is fairly close to the optimal point, but the EPC 8009 is a little to the right, but the curve relative is fairly flat. Both points seem to indicate that they should have comparable performance to each other, and we will see if that is true. Let's have a look at the experimental performances now between these various topologies. Before we get into that, I want to give you a background as to what we did. First, the operating setup. The source coil was tuned to be on resonance. That's very important because it enhances the efficiency of the overall system end to end. Operating off resonance, as you would in a traditional voltage mode class D, has a significant efficiency impact as you increase the circulating energy in the circuit. Device tuning is fixed and does not vary at all. Only the load resistance will be varied. The performance testing, we will have 4 conditions which we will test for. First will be a fixed load, variable supply to the amplifier, and this will be used to determine the absolute peak performance of the circuit. And this gives us a good indication to compare the various technologies and topologies with each other. The next test will be a fixed supply, and we will vary the DC load with a ratio of 3 to 1. This is our load variation test. The third one is when we use the circuit as a regulator. So the output voltage will be fixed and the DC load will be varied with the same ratio, and the corresponding input voltage will be adjusted to find that output voltage. Since we're doing this open loop, this will be conducted manually. And of course, lastly, the last test we will do is a fixed supply voltage, a fixed load condition, and we will then introduce foreign objects such as a solid aluminum plate and then determine the impact of that on the topology and the devices themselves. We'll get into that into a little bit more detail now, because that is a very complex and concept to understand. So what we're going to do is we're going to check on the device for overvoltage, overcurrent conditions, and overtemperature. It is important because each of these 3 can impact the performance of the circuit or even lead to failure of the devices. What we need to determine is the severity of a problem. We need to determine can it be detected, and of course the impact on the devices and system. And our test setup, we will use a fixed DC load resistance of 47 ohms with the device board placed centrally over the source coil, 1 inch from the source coil. And then we'll have 2 test conditions, one where we introduce a solid aluminum plate just barely above the source coil. In other words, we're trying to completely shunt out the source coil. And the second condition is we will place the source coil approximately 1.5 inches, 38 millimeters above the source coil. And in this case, it yields a near perfect mirror image current in the aluminum plate that has the worst impact on the coil performance, and we will then determine what will happen with the amplifier. Here is our experimental setup. As you can see, we have the coil set shown there. The source coil is the larger coil and the matching on the left-hand side, and the smaller coil is the device with the matching on the right-hand side. On the far right, we have our device board, which includes the rectifiers and smoothing capacitors and a load bank resistor that can be programmed for the various DC load resistances that we would like to test. The board also comes with Kelvin probe points, so we can measure the shunt current, and we can measure the voltage at very precise locations. On the left top, we have our Class E amplifier, as you can see there, and it has the shunt capacitance and connects to the coil with its RF choke shown at the bottom. The bottom left image is our Class E, our ZVS Class D amplifier. You can see that it's a significantly smaller portion in the center of the board, comprises the entire amplifier. Let's look at the experimental Class E case. The devices we evaluated we've already shown, but let's give some details. The EPC 2012 is a 200 volt device, 70 milliohm with a 5 volt gate. The MOSFET we will compare it against is a 200 volt device, 175 milliohm, that has the same output capacitance as the GaN FET, but uses a 10 volt gate. Here we have our peak performance for the Class E. The blue line shows the GaN FET and the red line shows the MOSFET. On the left we have our efficiency, and on the right we have the gate power. This is the actual gate power measured into the gate driver itself, and it's running just one device. You can see there's almost a 10 times increase in the gate power for the MOSFET compared to the GaN FET. And this has a significant impact on the overall efficiency of the converter. As you can see here, the GaN FET is significantly higher in performance and exceeds 80% efficiency from 12 watts and higher. This is all tested with a fixed load, DC load resistance of 20 ohms. Let's have a look at our load variation, and this is where it gets interesting. We have varied our DC load from 14.7 ohms to 47 ohms, and we fixed the supply voltage at 20 volts. And we can see the performance again, the blue line being the GaN FET and the red lines being the MOSFET. On the left we show the efficiency, and on the right we show the output power. This is because the power is fixed, it's much lower than in the previous case. Otherwise we end up with conditions that we can test because it exceeds either the thermal rating or voltage rating of the devices. As you can see, there is a slight shift in the operating frequency of the coil because the Class E does impact the resonance of the system. As you can see that the dashed line and the dotted line do not overlap perfectly. There's again almost a 4% difference in efficiency performance between the two amplifiers based on the GaN FET and the MOSFET. Next, we look at our load regulation. So in this case, the dashed black line represents the output power. So both converters will have exactly the same output power, and we set the output voltage at 15 volts. Again, for reasons that if we choose a too high voltage, we may come into conditions that we can test and have a good comparison over the entire range. Going towards the left, the DC resistance decreases, and the coil becomes capacitive as far as the amplifier is concerned. Moving to the right with a higher load resistance, on the DC side, the coil becomes inductive to the amplifier. As you can see there that the efficiency has a linear decay with increasing resistance, and this indicates that it's primarily driven by diode conduction losses, and as it goes down on the left, it is driven by capacitive or partial zero voltage switching losses. Again, we have about a 3 to 4 percentage points difference between the GaN FET and the MOSFET in performance. Let's have a look at the Class E amplifier for the foreign object test. In this case, we will just tabulate the results. We have the spacing again at 2 millimeter and 38 millimeter. And we look at the three parameters we need to for the device. That's the voltage, the current, and the temperature. For the 2 millimeter case, we are making the coil completely shunted out. In other words, the device, the Z load impedance becomes very high, and therefore the class E amplifier struggles to get current in the extra inductor. So the shunt capacitor dominates the switching cycle, and therefore represents a capacitor switching losses for the device. In this case, the circuit could not be tested to full input voltage and had to be significantly dialed back. The voltage across the device is now 6.4 times that across the from the supply. And if you remember, for the ideal case, it's only 3.56 times. So there's almost a doubling of the voltage across the device. And as we said earlier, this is one of the reasons why you have to choose a higher voltage rated device. The current drops because you're not really putting any current into the load anymore, and hence it drops. But the partial zero voltage switching condition presents a very high loss mechanism for the devices, and therefore the temperature rises very quickly and to very high levels that can cause failure of the circuit. For the 38 millimeter case, which is the worst case in terms of the coil presenting an issue, we see that we still have a very high voltage across the device, which is about 5.5 times that of the supply, but the current has gone very high. Now the problem with that is the current in this case is, for this operating condition, is high, and you might think it's detectable. But for other operating conditions, it is on par with being able to deliver under normal operating conditions on a different load setting for the amount of power you want. So it becomes difficult to use that as a metric to detect whether there's a problem. However, if you use the two together, and you say the voltage is high and the current is high, then you can say there's an issue. Hence the detectability, it becomes easier to do. The losses in the device are diode driven, as the coil presents an inductive loading to the circuit, and this also makes that the FET has higher switching losses, and in this case it reached 90 degrees C. So the severity in this case for the 38 millimeter is medium, where because it can be detected. However, for the 2 millimeter spacing, severity is high, as it is very difficult to detect accurately. So we have a poor device performance under both conditions, but this 38 millimeter case can be detected. Let's look at the thermal performance of the circuits operating under ideal conditions and delivering 29 watts into the load. On the left we have the GaN FET, and on the right we have the MOSFET and the corresponding gate drivers. As you can see, there's a significant difference in the temperature of the gate driver itself. And it just shows that the gate drivers for the GaN FET are not only well suited for operating at high frequencies, but they also work less hard driving the gate of the device itself. Let's have a look at the experimental results for the zero voltage switching class D. The devices evaluated, as a reminder, are the EPC 8009, which is 65 volt part and 138 milliohms of 5 volt gate. The MOSFET we compared that against is a 100 volt MOSFET with 100 milliohm of on resistance and a logic level gate of 5 volts. The EPC 2007 was also 100 volt, 24 milliohms on resistance, and has a 5 volt gate. And the last MOSFET we will compare that again against is a 100 volt, 43 milliohm with a 10 volt gate. So first again, we will look at the peak performance. For the circuit, we have fixed the load again, in this case at 23.6 ohms DC, and we will operate the circuit as far as we can. The orange line here shows the performance of the MOSFET number 3 with a 10 volt gate, and you can clearly see that at one point we couldn't continue the test because the gate driver had exceeded 95 degrees C. The efficiency is shown on the left, and we had a paltry 78% peak peak performance for this circuit. On the right, we have the gate power, which is as measured going into the gate driver of roughly 690 milliwatts. Now let's go compare that against the EPC 2007, and we were able to significantly improve on that, where we can get to just above 35 watts of total output power. And we can see there that that one's running at 5-volt gate, and we have a peak efficiency around 82.8%. Then we tested the EPC 8009 under the same conditions, and we can see that the significant drop in the gate charge has allowed the converter to operate even more efficient at the low power ends, and we do not take a significant hit for the increase in on resistance on the high power end. As you can see there, it comes up to on par with the EPC 2007, which is 24 milliohms versus 138. So from this we can conclude that the on resistance is not dominating losses, but it's the gate charge that is dominating losses. You can see there that we have around 150 milliwatts of total gate power consumption for the EPC 8009 device, which includes the overhead of the gate driver itself. And lastly, we have the MOSFET strong contender, in this case for the logic level FET. You can see that it did reach 35 watts, but it just didn't quite make the 82% mark in this test. The gate losses are comparable to that of the EPC 2007. Let's have a look at the load variation. In this case, we were able to complete the test for the power MOSFET number 3. However, above 25 ohm resistance, you can see there's a kink in the output power curve, the dashed line here. So we're losing output power by some mechanism in the circuit due to the high gate losses. Here we have the EPC 2007 device, and see that black dashed line is where we expect the output power to be for the circuit. And you can see a dramatic improvement in the output efficiency of the device under these conditions. Here we have the EPC 8009, and you can see it's improved on the low end as well. But on the high end, due to the higher output power, the 8009 is going to work harder, and has, because of the 5 times increase in on resistance, it then shows up on this curve. And lastly, we have the MOSFET, which is still lower than both the GaN FETs. Let's have a look at load regulation for the ZBS circuit. In this case, again, for the MOSFET number 3, we were unable to complete the test. As you can see there, going down in resistance here forces the circuit to try and push more power, and at some point the gate drive had exceeded 95 degrees C, so the test was halted at that point. The EPC 2007 shows that we were able to complete the test here, and the black dashed line shows where the power is supposed to lie. The performance there is very good, and you can also from there see that we had tuned our circuit to operate optimally at 23.6 ohms, because that is where the efficiency peaks. The same is true for the EPC 8009, and you can also see here that it too is showing a significant improvement over the EPC 2007 for the same operating conditions. And lastly, we have the MOSFET here, showing that the performance is still lower than the GaN FET, but on the high load resistance end, it has a lower on voltage for the diode conduction portion, and therefore that slope comes down at a lower rate. These are issues that can be easily fixed for the gate circuit for the GaN FET. Foreign object detection on the zero voltage switching class D topology. Again, we have our 2 mm, 38 mm case, and again, we're looking at voltage, current, and temperature. For the 2 mm case, which simply shunts up a coil, the coil impedance presented to the amplifier goes up dramatically. And in the case of the class D, that's not a problem, because we have the regular voltage across the device. The current in the coil went down so much that it's only driven now by the zero voltage switching circuit, so zero voltage switching is maintained. And therefore we have normal operation. We're just not putting any power into a load. The temperature of the devices remain cool, and the severity is therefore very low. If you remember, the severity was very high for the similar condition for the class E. For the 38mm case, we still have the same voltage across the devices as the supply, so there's no issue there. The current is half that of the normal operating condition for this test. We do have some hard switching condition present, but that is well within the capability of the FET. In the worst case, it was around 85 degrees C for the EPC 8009. So in this case, the severity is medium, but it's not catastrophic and can operate indefinitely under these conditions. So we have acceptable device performance under both these operating conditions and an inherent ability to operate under these test conditions. Foreign object cannot be easily detected by the circuit still because you have conditions that exceed that of a simple detection circuit. So communications are still required between the device and the source to determine if the device is legitimate or not. Let's look at the thermal performance between the circuits here. Because the MOSFET is a logic level, we use the same gate driver for driving the MOSFET. So we have the GaN FET, the 8009 on the left, and we have the MOSFET on the right. You can see there that the circuit's thermal performance is very similar. For the other two devices, the EPC 2007 compared to MOSFET number 3, we have very dissimilar performance results. We had to use a comparable gate driver that can operate the MOSFET at 10 volts. Both gate drivers have built-in bootstrap circuits, and you can see on the left we have the GaN FET operating at 35 watts, and the MOSFET was only able to do 17 watts and was already exceeding 95 degrees C in the gate driver. So wireless energy transfer topology comparison. Now we're going to look at the two topologies and compare them against each other again for peak performance, load variation, and load regulation and foreign object presence. Here we have the two topologies based on the two best devices, the EPC 8009 for the zero voltage switching converter and the EPC 2012 for the single-ended Class E. In this case, we presented the results for both two load conditions for the Class E amplifier, because the EPC 8009 was measured at 23.6 ohms and the EPC 2012 was done at 20 ohms. So to compare the results for the two, we made them similar. And you can see that it has an impact on the performance of Class E, and it shows that variations of the load on the Class E has a significant impact on the performance of the circuit. And as you saw that earlier, that bell curve was very sharp for the Class E topology. Here we have our load variation comparison with a fixed supply between the Class E and the zero voltage switching class. You see that the ZVS Class D has a nice nearly linear increase in output power as the load resistance increases, and we have a pretty high efficiency overall on the entire design. And what's important to note is for this particular range, we have similar power losses or efficiency on both ends of the load variation. However, that's not true for the Class E, because it has to be designed at the lower resistance end in order to make sure that it can operate with the highest efficiency across the board. So we lose the ability to push the amplifier with a lower DC resistance on the left-hand side. As you can see that above the design point, in this case, which is around 20 ohms, the performance, the output power also decreases as the circuit is no longer operating optimally. So you lose a lot of output power at that point. Let's look at the load regulation comparison. Here we can see that between the two, we had to operate the single-ended Class E at a reduced power to be able to get the results out. They have similar type of performances, but you can see there that there is a significant difference between the output performance efficiency of the two devices, between the two topologies. Let's look at the summary of the foreign object immunity. The ability to operate in the presence of a foreign object, the ZVS Class D, is very good, as we showed that it has inherent ability to operate, whereas the Class E is very bad and requires special intelligent control to make sure that the foreign object does not cause major problems for the Class E. No topology has a simple means to detect the foreign object, but that's not a problem for the ZVS Class D. So in the future, probably some improved controller ICs can build in some multiple methods to detect that without communications. Here we have a summary again, and just to show that the 2mm case is bad for the Class E. The ZVS Class D is good overall with the 2mm case. And at 38mm, both converters have a slight issue with it, but in the case of the ZVS Class D, it can operate indefinitely. So what's next for wireless energy transfer? Let's look into the future. EPC is developing new demonstration boards based on the single and differential versions of the ZVS Class D amplifier, and they can operate at both 6.78 megahertz and 13.56 megahertz. We've done a lot of work to understand how these circuits work, and we've included a pre-regulator so that when the coils are operating and you remove the device completely, the regulator will then just take over and prevent the circuit from operating with too high losses, and it works very well, and the circuits can operate without intelligent control. We'll also be looking at providing a single and differential mode Class E amplifier for those who are still interested in using that, and we're showing that even the GaN FET can still show enhanced performance over a MOSFET for that topology. There will be improvements in coil technology. The wireless standards have just started, and we have many years to go, and that will change, and the efficiencies will go up, technology will improve, and it will drive this even further and faster. An GaN FET specifically designed for wireless power. Now that we know a lot more about wireless power and how to operate it and what the issues are, we have our wireless power figure of merit. We can use that now to come up with a optimized half-bridge device that is suited for the zero voltage mode Class D, or a dual common source FET version for the Class E. And this is for differential mode. So these FETs will be optimized specifically for wireless power and therefore maximizing the efficiency of the circuits. Here we can show some of that using our wireless power technology transfer figure of merit. And for the ZVS Class D topology, we can compare against the best MOSFET technology against the 65-volt GaN FET technology, and you can see that optimizing the FETs will show at least up to a 50% reduction in the losses. That is significant. So there's room for improvement on both, but you can see that the MOSFET technology will never be able to come to the level of efficiency as the GaN FET. Here's an image of our new wireless topology demonstration board. It's based on the A4WP standard class 3 source coil and category 3 coil set for the device, and the amplifier shown on the left there simply connects to them. The coils are pre-tuned so that you can simply evaluate the circuits. It includes a pre-regulator and is capable of both 6.78 megahertz and 13.56. Although not many people are using the A4WP coils right now, but you can use your own coil if you want to operate at 13.56 megahertz. And in summary, GaN FETs are disruptive in wireless energy. They are higher efficiency than MOSFETs, and that's a big deal for them. They can operate at both 6.78 megahertz and 13.56 megahertz, and that's primarily driven by the significantly lower gate charge they have compared to MOSFETs. They're also low profile, which is, as we mentioned, required for wireless energy, particularly in the commodities market with mobile devices. They're easy to use. They are just like a MOSFET, so they are fairly useful and easy. And we have a lot of material on our website that you can read up on to learn how to use them. They drive new topologies, and a good example is the ZVS Class D topology for the wireless. Thank you very much, and if you have any questions, let us know.
Thank you.